Okay, so hi everyone. My name is Mischa Knabenhans. I'm a PhD candidate at the University of Zurich. I'm also working in cosmology, so there will be quite some overlap with the past two talks. I'm sorry. But for those of you, if there is someone who hasn't heard the previous talks, just going to quickly review. So some of you might still think, like, what is the cosmic energy density field? Let me just set the stage. We start with Earth, zoom out. There is the solar system. Zoom out one more time, then we see the galaxy. Our galaxy is the Milky Way. This is Andromeda Galaxy, which is our neighbor. I guess so far this is quite familiar. But then there are these dark matter halos. Fortunately, Dr. Ho has already introduced dark matter, so I don't have to do this again. The galaxies, like the Milky Way or Andromeda, would reside in these central black regions that you see here. By the way, this is a simulated dark matter halo simulated by one of my colleagues at the University of Zurich, Doug Potter. And these dark matter halos, they are invisible clumps of matter that tend to arrange themselves in this cosmic web that we've already seen a couple of times today. And these reddish balls from the last slide now correspond to these tiny yellow dots here, so such that you have like an imagination of the scales, spatial scales that we're looking at. And the black or dark regions are the high density regions, and the bright or even white regions are the voids or low density regions. And this is why this is the density field that I'm referring to in the title. Now, as we've already heard, again, this density field encodes lots of information about fundamental properties of the universe, such as how much matter is there, how much energy is there in the form of radiation, how fast did it expand over the past couple of billion years. And when we cosmologists try to learn something about the universe, this most often means that we try to acquire really precise knowledge about the values of these fundamental parameters. And just for future reference, these parameters play the role of features in what I'm going to talk about in the next couple of minutes. But before we get to the machine learning part, we do not look at the density field directly. We actually do consider the statistics that have been mentioned in the past. Slightly different one, or a slightly processed statistic than just the power spectrum that has been mentioned. But what we're trying to find is a map from the cosmological parameters, so from the feature vector you see on the very left side to these statistical measures that are the targets. Now, there are two options how you can find such a mapping. The traditional ways to run the simulations, but as has been mentioned, this is really, really expensive, depending on the resolution, of course. We're trying to focus on high resolution simulations. That's why for us they are really expensive. And sometimes the high resolution just renders certain applications prohibitively expensive. And for these cases, there are these machine learning applications that try to bypass the expense that you would have to afford with the simulations. And in our community, they're usually referred to, these machine learning applications are usually referred to as emulators. And there is one emulator which is called Euclid Emulator, which is the result of my PhD work. And unlike many of the talks before, we do not use neural nets. We use a technique called polynomial chaos expansion. For those of you who are not familiar with this, it is a supervised learning technique based on orthonormal polynomials. And I'd like to point out just two properties which are particularly important to me. One of which is that since the generation of data using simulations is so expensive, we need to be able to get away with only very small training data sets. So there is no way how we could use or produce thousands of simulations and training data examples, no chance. And it is not really a black box because we can really study this PCE and have a statistical interpretation from it. And just as a side note, we use a MATLAB package called UQLab. written by our collaborators at DTH, and I encourage you to have a look at it. So let me go a bit deeper into the training pipeline. So we start out with a predefined parameter box. We sample it in the Latin hypercube way for each instance of the parameter vector. We run the simulation, we measure the statistics, and for technical reasons of the algorithm, we then decompose this into principal components. And what we're actually doing is we then map the feature vectors to each of the principal component weights we decide to retain in our model. This is actually one of the hyperparameters of this approach. So in the end, basically this polynomial case expansion is really just a sum with the polynomials here and a coefficient that you're trying to learn. We do this using a lasso loss function in order to sparsify the result. And let's look a bit at the configuration. So from Euclid Emulator, there are two versions. Version 1 is actually public. It's been published about a year ago. And it maps a 6-dimensional feature space to 11 principal components. And for this, we just use 100 training examples. So then for the last 15 months or so, I have been working on an update. We have added more physics. So for the physicists, we have added dynamical dark energy and neutrinos. So this means that we have like now an 8-dimensional feature space, and we map to 14 principal components or a 14-dimensional target space. And for this, we train on 127 examples. So now, how does this perform? This is just for Euclid Emulator 1. Again, we need to generate the validation examples using simulations. So this is again expensive. That's why there are only 36 validation examples and not much more. However, we are working in precision cosmology. So this means that the requirement is that we can predict our statistical measures with an accuracy of 1%. And in the lower left corner of this slide, you see a plot where we compare predicted to actually simulated statistical measures. And we managed to beat this requirement of 1% by about a factor 3. So we were happy with that. Actually, on the left-hand side of the plot, there is a region where it is not really a challenge to get to this accuracy. However, on the right-hand side, it becomes really challenging. In terms of speed, simulation of the quality that we used for training takes about 10 to the 4 CPU hours per simulation. And when we actually evaluate the emulator on just a laptop, then it takes about like 10 to maybe 100 microseconds. So we get a speed up of about 1 billion. I have mentioned that there is a possibility to investigate the statistics of polynomial chaos expansion. This can be done using a method called Sobol analysis, which is a sensitivity analysis. And when you have your sum in your polynomial case expansion, you basically can just take it and reorder the terms in a predefined way. And this gives you information about the feature importance. And here the plot on the right-hand side actually is the result for Euclid Emulator 2 and for like the different principal components. There will be like 11 others, but I have chosen to just plot the first 3. And this can come in really handy. I have applied this in another scenario that maybe Miles is going to talk about in the next talk, where we have a multi-stage training procedure, and there I can use it for feature selection and so on. This brings me to the end of my talk. I hope I could spark your curiosity in the strategy of polynomial chaos expansion and Euclid Emulator in particular. I encourage you to check out the GitHub page where you can look at it a bit more closely, or if you're interested in the theory behind it, then have a look at the paper. And I'd be really happy to talk to you if you're like interested in it. Thank you very much.